Hello everyone, welcome to what will be our pre-lecture for lecture number 32 here. We're going to talk about rate laws as they relate to chemical kinetics. So before break, we talked about kinetics. Generally speaking, it is how we mathematically describe the rates of chemical reactions. So as a reaction progresses, our concentrations of our products will decrease, concentration of reactants will decrease, and concentrations of products will increase. And we're going to take another step to define that mathematically today in this video and then in class. And so typically, the best way to describe these is using something called rate laws or rate equations, you may see. These are mathematical expressions that describe the relationship between our concentrations of our reactants. And so key thing here, when we're doing a rate law, we define things in terms of the reactants. And so in this situation, we have A and B going to B or going to some type of product. And so with this, something I want to point out here, when we write the rate law, our rate is always going to be the left side. We have this new variable k, lowercase k, so we've been dealing with uppercase k all semester. We're now dealing with lowercase k, that is our rate constant. We have the concentration of A, concentration of B, and something I want to point out here is we have superscripts, M and N. These are going to be usually some whole number, usually 0, 1, 2, or 3. They can be half numbers, but that's slightly more complicated than we'll probably get in this class. And the key thing here is that M and N are not necessarily equal to A and B. So we can't, from the stoichiometry alone, determine what our basically superscripts are going to be there, our exponents. And so again, K is going to be our rate constant. This is going to be temperature dependent and not concentration specific. So in what we talked about before break, our rate changed as a reaction progressed. Our rate constant is always going to be the same, no matter what our concentrations are, as long as we're at the same temperature. And then M and N, in addition to being exponents, we would call them reaction orders. Okay. And again, those are typically 0, 1, or 2. And a key thing with them is they must be determined experimentally. And we do that by varying the concentrations of reactants and measuring how the rate changes. Then we have what we call the overall reaction order, which is the sum of all of those reaction orders. So essentially, in this case, M plus N. Okay? And so if we were to experimentally determine a reaction order, then we would want to, sorry about that, be given something like this, where we have a set of data, and say for some generic reaction where we have 4A plus 3B going to 2C, we collect this data at a constant temperature, and I ask you what is the rate law for the reaction and what is the rate constant, and make sure you include the correct units there. So what we would do, what I would recommend doing first is always writing out just a generic rate constant for your reaction, or rate law for your reaction rather. So rate is always going to be on the left side of our equation. So our rate is going to be equal to some rate constant K that we're going to be able to solve by the end of this reaction. Then we define terms in things of the reactants, so times the concentration of our reactant A to some power M multiplied by the concentration of B to some power N, right? And that would be just our generic rate law. And then the data that we're given, we're usually given concentrations. So you'll see here we have our concentration of A, here we have our concentration of B, and then we have a measurement of our rate in units of molar per minute, okay? And so what we can do is basically plug in these values and solve for the variables that we don't know. And so let's just take the first two trials, do trial 1 and trial 2 here. And I'll show you the strategy for how to solve these problems. Something that I like to do is look at the rate that is highest, in this case 45, and put that on top. So if we say 45.0, it's going to be equal to, we don't know what k is yet, so we're just going to leave that blank. The reason I should say I plugged 45 in here is because that is equal to our rate. Our concentration of A, in this case, or initial concentration, these are initial concentrations, is 0.300. And then we don't know yet what our exponent or our order for A is going to be, so I'm going to leave that in as variable. Concentration of B is 0.100 to some power n, and that is, at this point, all we know for our rate equation. And so that is one trial, and if we look at this reaction, we have 1, 2, 3 things that we don't know. And so if we were in an algebra class, I would probably tell you, well, we need the same number of variables as we have equations. Another thing we can do, so I will tell you that we need another equation, but one thing we can do is let's look at trial 1. If we pick a trial that has the same concentration of one of our terms, then we know that will go to 0. And so, so this is trial 1 here. If we were to write out trial, or pardon me, it's not trial 1, we started with trial 2. This is trial 2. If we write out trial 1 as well, our rate is 5.0. That'll be equal to, we still don't know k. This time our concentration of A is 0.1, still don't know m. And our concentration of B is the same, 0.1 to the n. And so now we have 2 equations, 3 unknowns, but with our B term, 0.1 to the n is going to stay the same in both of those equations, right? So we can cancel those out. And the easiest way to solve this is to actually divide these equations by each other. So that's one way we can cancel out. K is going to be the same for both of these, so that is not going to change, so we can cancel those out. And that simplifies things a lot for us. For where now we have, so we can do a little math. 45 divided by 5 is equal to 9, right? And that is going to be equal to, if we do 0.3 to the m divided by 0.1 to the m, that essentially just turns into 3.0 to the m power. And now we have one equation, we have one unknown. And so we can solve for m. And so the way we solve for m, in case you don't remember how we deal with logarithms, is we take, or how we deal with exponents is we use logarithms. So if we take the log of both sides, we end up with log of 9.0 is equal to, and when we take the log, we can move our exponent down. So m times the log of 3. And then if we want to isolate m, we just divide each side of our equation by log of 3. So if we divide this by log of 3, then we would end up with m is equal to and the log of 9 over the log of 3. And if we were to write that out, sorry, log of 9 over log of 3. If we were to put that into our calculator, we should get that m is equal to 2. Okay. So that is how we would solve for m. Now we know m, so good news is you can do the same method using different trials to find out what n is. And once we know what n is, we will know rates, we will know A, we will know M, we will know B, we will know N, and so our final thing is we can solve for K and figure out what our units will be at that point. And we will pick that up there in class, but this is how we start that problem, so I wanted you to see that heading into class. That's it for this pre-lecture. If you have any questions, please do let me know. Otherwise, I will see you soon.